Okay, and in study goal number 21, we need to talk about the ocean. Now, it's pretty cool that we live here because UCSB has been a world leader in this research. A lot of the most important research about climate change in the ocean comes from UCS Brodog. There's a few different things that we need to discuss about the ocean. First is the fact that the ocean holds more heat than the land or the air. That's because water has a higher specific heat capacity. You may have heard this in the 7th grade or something. So you might know that I can walk around in trunks if it's 75 degrees and I'll be perfectly happy because it's easy to keep myself warm in 75 degrees. The air doesn't take my heat very well. But if you're in the water, you're in contact with a whole bunch of water molecules. Same wobble concept. So if you're in water, the water can take your heat very, very well. That energy transfers to water very easily. We say that water has a higher specific heat capacity than air. So 75-degree air is perfectly comfortable, but 75-degree water, you would die of hypothermia in probably a couple of hours, depending on how much body fat you have. Now, because water holds heat better than the air, one thing that you need to know is that most of our new heat, our global warming, the amount of new heat that we're now holding, most of that is in the water. About 90% of our new heat has gone to the ocean. We're not really heating the air and the land very much. You don't really feel huge changes, but we are heating the ocean very, very much. Because water has a higher specific heat capacity, it also stays hotter longer. It has more thermal mass, it has more memory of temperature. So once humans are gone, it'll take 600 or 700 years for the ocean to get rid of all of its heat. You might know that water bags are a nice way to stay warm. I know that Americans don't really use water bags, but I grew up in a country where heating was very expensive, so you'd heat up a bag of water. You put boiling water inside of a rubber thing and you wrap that in a towel and then you go to bed and you use that to keep you warm. Water bag, the ocean works like that. So once you heat up land, it cools off pretty quickly. And you heat up air, it cools off really quickly. But you heat up water and it stays hot for a long time. We don't experience too much of our heating because the ocean is heating and then it's going to stay warm and radiate that heat back to us for a long time. Something else that's interesting is when the ocean is hotter, it evaporates more. So we are living in what's called a swamp Earth, meaning a hotter ocean is making more water vapor and more clouds. This is a fascinating change. As the ocean is hotter, we're making more clouds. And there's interesting information about how those clouds affect climate. We'll get back to that later. So hotter planet makes a wetter planet. And finally, another thing about the temperature is that hotter water is bigger water. So you might know that heat affects the kinetic energy. So those water molecules are moving faster and bouncing off each other more. So hot water grows. That's called thermal expansion, and you have to know that term. And what that means is that on a hotter planet, the ocean gets bigger. And most of sea level rise is not from new water. It's not from melting ice caps. It's not from the glaciers. Sure, we are adding water to the ocean, but that only raises sea level a little bit. Most of rising sea level is because the ocean's getting warmer. And you have to know that thermal expansion is the primary driver of sea level rise. On a hotter planet, we just have more ocean. We can track how much the ocean has heated up, and it's been a lot. And if we look for where all the energy has gone, if you take the total change from man-made warming of the earth, that is mostly found in water. Very little is found in the ice caps, on land, or in the air. So the first thing to talk about the ocean is the temperature changes. The second thing to talk about the ocean is that it's a place where carbon leaves the biosphere. You remember a sink. We saw this in a previous study goal, where of all the CO2 that we've added, that has to go somewhere. So some of that CO2 is still in the atmosphere, some of it is locked up in biomass on land, and some of it has sunk to the ocean. Keep in mind, anything that becomes a carbon sediment and sinks to the bottom of the ocean, once you cover that up with other sediments, is now locked up for good. So an interesting thought is that we are making carbon-rich sea bottom deposits all over the earth in just a couple of centuries. In other words, someone's going to find a lot of fossil fuels in 300 to 500,000 years, or 300 to 500 million years, whatever the number is. In a long time, all these carbon-rich deposits will mean that there's a whole bunch of carbon locked up later, right? Ocean is a place where you sink carbon. And that's important for you to know. And it's also important for you to know how that changes. So the last thing we need to talk about is a phenomenon that was discovered here at Santa Barbara. You must know the recipe. Water plus oxides makes acids. I think I mentioned that before when we were talking about acid mine drainage. And water plus carbon dioxide makes carbonic acid. You have to know that recipe. So when we add more CO2, that's going to mix with water to make more acid. We are making the ocean more acidic. That's called ocean acidification. Ocean's becoming more acidic. And it turns out that is a huge deal. For one thing, life is really sensitive to pH. So no matter where you live, your body can tolerate a lot of temperature, because temperature does go up and down all the time, right? On any given day, temperature goes up or down 20, 30, 40 degrees. If you're like a fish, you can take it if the water goes up a couple degrees or down a couple degrees, because that happens in nature. Temperature is plastic, so our bodies tolerate a pretty wide range of temperatures. Here's something interesting. On an evolutionary timescale, pH does not change in the ocean. The acidity of the ocean does not change every day. It's a huge body of water, right? So the acidity of the ocean is very, very precisely consistent for lifetimes and lifetimes and lifetimes. So evolution has made ocean life tolerate a variety of temperatures, but no life tolerates a variety of pH. You see, if I raise the temperature in your room by 20 degrees, you might break a sweat. And if I drop the temperature by 20 degrees, you might start to shiver. But if I change the pH of your body by 0.01 pH points, you would die immediately. And so all the extra CO2 is making all this extra acid in the ocean, and the ocean is leaving wildlife's tolerance for pH. pH affects all chemistry. Chemistry like our nervous systems, the regulation of our heart rate. And so things that live in the ocean are getting really screwed. Ocean acidification is a way bigger problem ecologically. It's about tolerance. You should probably write that down. Species cannot tolerate changes in pH the way that they can tolerate changes in temperature. So ocean acidification is very destructive ecologically. It also really affects us. So here's the last thing you'll need for number 21. This compound, calcium carbonate, Ca for the calcium, CO3 for the carbonate. This is the compound that makes shells, so snails, bivalves, lobsters, crabs, the skeletons of corals. If you keep fancy saltwater aquariums, you might know you can buy puka sand, which is like a coarse, very light, ground up seashell. Or you might know that like there was this 1980s jewelry trend, which was like Hawaiian puka shell jewelry, which are little notched pieces of shell with a hole in them. That's calcium carbonate, the chemical that makes shells. And there's not a lot of stuff that eats shells. So as shells get broken up, they settle to the bottom of the ocean, and that's where the carbon goes. That's the carbon sink. You have to know that. See, right there, that's the carbon, right? That's a carbonate. That's a C for carbon. Carbon. So when things grow in the ocean, they make more shell. When that shell gets broken up and dies, that's carbon that's left the atmosphere, dissolved in water, locked up in life, and now is going to become rock. That's a sink for carbon. Calcium carbonate is how carbon leaves the biosphere. So, you know, if we were growing a whole bunch of shells and we ground them all up and dumped them into the bottom of the ocean, that would take carbon out of the atmosphere and sink it away. That would help us solve carbon pollution. But there's this wacky thing that happens in chemistry, and I wish I understood it well enough to explain it, but I'm not that smart. So you're going to need really good notes on this one last thing. When the ocean has more carbonic acid, there's less carbonate for the calcium to bond with. I don't really know how to explain that. I'll show you a diagram soon so I can repeat this. But we do know that when the ocean gets more acidic, those shells don't grow as quickly. In some cases, they stop growing entirely. So first of all, that's huge impacts on the ocean food web, right? Think of all the food chains in the ocean that start from something with a shell. Like little stuff, like krill makes shells. So that's a huge change to ocean food chains. Second of all, when the ocean becomes more acidic, less carbon is sunk because the shells grow more slowly. I can't explain that well, but you'll need that. So look, when we have normal carbon in the atmosphere, we don't get a ton of carbonic acid, so most of the carbonate goes into shells. But when the ocean becomes extra acidic, we get more, when the atmosphere becomes more rich in carbon, we get more carbonic acid, which means there's less carbonate becoming shells. That's a lot of notes, and I'm sorry for this mix up today with the videos. I'm going to stop recording now.